everyone, I'm Hanlei Zhang. I feel very honored to be here to introduce our work. Nowadays, deep learning has been widely applied in various domains, such as face recognition, machine translation, self-driving, medical diagnosis, and so on. However, it also faces serious security threats, particularly backdoor attackers. This attacker cause model to behave normally on normal samples, but malfunction on backdoor samples. This backdoor attack can result in serious consequences. Therefore, we need a method to detect it. However, existing backdoor attackers can be categorized into different types. The initial version is the source or sample agnostic attackers. Source refers to samples have the same label, and the source or sample agnostic attackers can change all sources or samples into backdoored ones and mislead the model. However, the source-specific attackers can only poison special sources rather than all sources. And the sample-specific attackers can generate different triggers for different samples, which means one trigger for one sample. And the consummation of these backdoor attackers is gradually increasing. And in addition to this classification, if the attacker knows the principle of certain detection method, they can generate a special trigger to effect detection. For example, if a defender targets at inverting a very small triggers, then the attacker can make their trigger bigger to effect detection. And the consummation of these backdoor attackers is more targeted for certain detection methods. And we list some representative detection methods and find that existing detection methods fail to identify advanced backdoor attackers, especially sample-specific and adaptive attackers. Therefore, in order to improve the detection method, we conduct research on the effectiveness and consummation of backdoor attackers. Let's take the sample-specific attacker as example. The effectiveness refers that the fitting sample A can be changed into backdoor sample and make the model malfunction. However, the consummation refers that if we attach the trigger of the fitting sample A to another sample B, then the generated sample cannot result in wrong model output. And if we separate the model into two paths, we can observe that these samples are first transferred to the first few layers of the model, which perform like a filter extractor to extract the latent representation, which contains the information of both the slope side and the trigger. Then the latent representations will be transferred to the following few layers of the model, which perform like a classifier to output the model results. And if we look back at the end process, we will observe that the two latent representations are very similar, with the benign part experiencing the stop side and the backdoor part experiencing the trigger. However, they result in entirely different model output. It's obvious that trigger plays different roles in the two scenarios, and for the fitting sample A, the trigger forces the model to output the wrong label, which means the tiny content of the latent representation can tamper with the model output. However, for another sample B, the tiny content loses its ability to tamper with the model output. And in our opinion, we think, compared to other latent representations, maybe the backdoor path can play a decisive role, which means they can at first decide whether to output the wrong label, and if not, it's the turn for other paths to decide which label to output. And if we can reflect the effectiveness and consummation, we can detect all these backdoor attackers. Both the effectiveness and the consummation are reflected in the ability of latent representations to tamper with the model output. Let's take two latent representations as example. We should notice that the stop side A is the fitting sample of the trigger. And if we take out a small proportion of phi k and taking the remaining part from phi b to generate a new latent representation as a formula and input it into the model, then when the beta is very small, the confidence score of the wrong label will be very high and the confidence score of the stop will be very small. However, if we keep increasing the beta, the confidence score of the stop side will also increase. However, considering the effectiveness, there exists a strong link between the trigger and the wrong label, so the upwarded process will be very small, and only when the beta has reached a very large value will the confidence score of the two labels be equal, and the very large beta reflects the effectiveness. And what would happen if we replace the phi k from the ficting sample A to another sample B? The initial situation is very similar. However, considering the concealment, the strong link between the trigger and the wrong label will decrease sharply as the beta increases. And in that case, a very small beta is enough to make the truth score equal, and the very small beta reflects the concealment. Therefore, we propose a new metric named relative computation score, which measures the ability of latent representation to tamper with the model output. And the calculation process is the same as before, and we will calculate the minimal proportion to change the model output, and we name the minimal proportion as relative computation score. And to demonstrate the effectiveness of relative computation score, we conduct experiments on 10 classification datasets. As we can see in the picture, the label 0, which we have marked in red, is the target label of backdoor attackers, and each little square represents the beta value of a latent representation pair. And as we can see, all backdoor attackers show the characteristics of effectiveness or concealment. And therefore, these experiments demonstrate that relative computation score is a robust and effective detection method for all kinds of backdoor attackers. However, we still have a problem to solve, which is, as a defender, it's very difficult for us to directly access the backdoor samples to calculate the backdoor latent representations. Therefore, we propose a model inversion method to infer the two sides of latent representations, and we use the input sample to represent the meaning of the latent representations. And the first set is more biased towards the benign latent representations, and the second set is more biased towards the backdoor ones. Therefore, we can transfer the calculation of relative computation score to these formulas and free it from the need of backdoor data. What's more, we also propose some abnormality indicators to distinguish backdoor, and we rely on a few non-benign models to calculate the benign boundary of these indicators. And we conduct extensive experiments to demonstrate the effectiveness and the robustness of BARBIE. We demonstrate the performance of BARBIE on source-agnostic attackers, source-specific attackers, sample-specific attackers, and clean label attackers. And in the second scenario, we propose two kinds of adaptive attackers. However, they fail in evading detection by BARBIE. What's more, we also conduct experiments on large datasets to demonstrate that BARBIE can maintain excellent performance on large datasets with a large number of classes. What's more, we also conduct experiments about fission transformer and self-supervised learning to validate the scalability of BARBIE. What's more, in some practical scenarios, model resources may be untrustworthy or limited, Therefore, we take two practical scenarios into consideration. In the first scenario, we think that maybe our models, benign models soon may be poisoned by some backdoor models. And in the second scenario, we try to detect the backdoor models with substitute models, which only have the same model structure. And BARBIE maintains excellent performance in these practical scenarios. In a conclusion, we have three main innovative points. First, we design a new latent separability metric in the relative computation score. Second, we compute it in a data-free manner by inverting latent representations. Third, we conduct comprehensive experiments to demonstrate the effectiveness and robustness of BARBIE. And it's the content of our paper. Thank you for listening.
Yeah, thanks for the presenter. We have time for 3 to 4 questions.
Thanks for presentation. I just want to clarify, for this detection, it is a sample level detection, or it is just to detect the model is backed or not?
It's a model level detection.
In this context, what is the computational overhead?
Overhead?
Computational overhead. So the cost, computational overhead.
Computational overhead. In our experiments, we found that sample detection method and model detection method are very different, which means sample detection method cannot detect model, and the model detection method is also harder to detect sample.
Yeah, but what is the cost? So how long it take to detect this backdoor?
It depends on the model. A simple model costs very limited time, like several seconds. However, for a more model with more layers, it may cost more time, like an hour.
All right, thank you.
Hi, this is a great work on backdoor scanning. So my question is about the adaptive attacks. So it seems that your method simply inspects the classifier part of the models. It is similar to free ego, the prior work. So my question is that if the attacker just replaces the classifier part of the model to clean pre-trained ones, and when the attacker trains the backdoor, it just injects the backdoor in front of the classifier part. Injects the backdoor into the feature extractor. So can your detection method detect the backdoors in this case?
Adaptive attacker. We also propose some adaptive attackers. However, I think it's very difficult to propose adaptive attacker target our method.
Okay, thank you.
Yeah.
Okay. Thank you for great talk. I have a simple question. Several specific backdoor attack can reduce the difference between benign sample and malicious samples. So such a can attack reduce difference in latent space of machine learning models when the trigger is given. So is this method can also able to detect such kind of attacks?
Products.
Maybe you can clarify your question once again.
Okay. So for example, so demo in the variant in Usenix 2022 is a kind of backdoor attack that can reduce the difference between malicious sample and benign sample in latent representation. So this means that several backdoor attacks can control the latent space for both malicious samples and benign samples. So my question is whether your method is also applicable to detect such kind of attacks.
Maybe we will calculate a benign boundary of these indicators, and the backdoored ones will, the indicators of the backdoored models will not in the boundaries, so we can distinguish this.
Okay, thank you. Can we discuss right now?
Okay. Thank you.
Yeah, thanks for the presenter.